Do you need to back it up a few? Do you have control?
No. They're trying now. Do I need to stand here? I have to stand here. Yeah, it works.
Oh, yeah, right over there. Okay. Is somebody gonna? What do you need this?
I don't need this. Good afternoon, everyone. Thank you for making it here. My topic is the impact of aviation, electrification on power grid and jet fuel industry. So I'm going to analyze how electric aircraft affect the power grid and also jet fuel, and also how it will help to reduce carbon emissions. Electric aircraft has been a high profile in both academic and industry. The primary concern is environmental concern. In the US in 2018, the jet fuel burns produced 251 million metric tons of carbon dioxide emissions, and it has been predicted it will grow at 4.5% per year. Also, the small aircraft, which consume 100 low-git, will also produce lead emission. Aimed at such concern, NASA have set ambitious goal that for the N+3 generation electric aircraft with an entry into service date from 2030 to 2035, the jet fuel consumption will reduce by 60%. But such ambitious concept relies on advanced technology that may not exist by the time 2030. So timing is an important factor in the electrification in aviation sector. It will start with small aircraft. Some electric small aircraft has already exist and today, such as the Alpha Electro and Aegis from Aviation. Aegis. It has also been identified the short-range opportunity exists in regional jets and the narrow-body aircraft section. But for the wide-body aircraft, the electrification will not happen in the near future. The fundamental challenge comes from the battery technology. Currently, the battery specific energy is around 50 times lower than the jet fuel specific energy. We can understand it by the two examples. If you want to maintain the same takeoff, if you want to maintain the same range of an aircraft, then the maximum takeoff weight will increase by 49%. But if you want to maintain the same takeoff gross weight in your aircraft design, the maximum range achievable will decrease from around 3,000 miles to 384 miles. Except for the battery, when you look inside the hybrid electric aircraft propulsion, challenge also comes from megawatt level motors. And also outside the aircraft, we also need charging infrastructure, flight control, and safety and certification process to make an electric aircraft to take off.
Excuse me.
Yeah.
Could you go to the other side so we can see this slide? There we go. Thank you. Kevin doesn't need to see. He's got a screen there to watch.
Yeah.
And to determine the electric aircraft rollout paradigm, we also need to take a look at the predictions of battery development in terms of battery specific energy and battery cost. The left panel shows the prediction done by NASA. Currently, the battery specific energy is only 250 watt-hour per kilogram, and a 400 level is an achievable goal by 2025. The 600 level is achievable by 2030, but beyond 1,000, it will not happen in the near future. In terms of battery cost, it has reduced significantly in the past decade, which will help make electric aircraft become realistic. Now suppose we have solved all the technology obstacles, but electric aircraft may come at a premium cost. Suppose we have a fleet of conventional aircraft. A realistic way to integrate electric aircraft would be only replace a small portion of the conventional jet fuel-powered aircraft. But here we want to kind of perform the worst-case analysis and suppose whatever the flight is feasible to be replaced by the electric aircraft, we would suppose the electrification happens. It has been identified the hybrid, in particular the retrofit hybrid electric commercial transport aircraft, will happen before the all-electric commercial transport aircraft. And even in the hybrid electric section, we might first use electric propulsion during climb and takeoff mission only before we use it to propel the whole cruise mission. Because of the penalty of the battery-specific energy, the maximum range achievable of an aircraft is reduced greatly. So we need to decide on the set of flights that can be covered by the electric aircraft. For example, we plot a histogram to demonstrate how much flight demand can be covered by the electric aircraft. It is shown for the regional jet section, a medium flight distance is 409 miles. And for the single-aisle aircraft, the medium flight distance would be 867 miles. And if we compare that number with the top left chart, we would notice the proportion that can be covered by electric aircraft is reduced greatly. So we need to reform our data set. Here I will use an example to demonstrate how to calculate the energy consumption for one flight leg. We use a matrix named the battery energy consumption per passenger per miles. So the battery energy consumption for one flight is the number of passengers times the flight distance times battery energy usage per passenger miles. Our data set provides us with the tail number from which we can get the aircraft model and then determine the battery energy usage per passenger per miles. Under our assumption that the flight schedule remains the same as the current flight schedule, we can calculate the charging power needed by the energy consumption for one flight divided by time duration during which the aircraft stays at the airport.
Could you tell what is the typical watt hours per passenger mile?
It differs from between regional jets and the single aisles. So typically, and also the hybridization level. For example, for 12.5 hybridization level and also under the assumption of battery specific energy being 500, the watt hour per passenger miles is 30, around 30.
How do they compute that?
It's adapted from another paper published by a student from aerodynamic.
So it's probably from actual.
No, they make a simulation of, they design their aircraft and simulate it to get this number.
So that's just the jets plus all the other goodies that are on the plane, right? The radios and it's everything.
It will include all the weight of
Yes, it has included all of it. Yes. Similarly, we can calculate the fuel consumption of one flight leg. Here we need this member because it's a hybrid electric aircraft, so it will also consume jet fuel. Our first result shows the aggregate annual electricity demand of hybrid electric aircraft at O'Hare International Airport. The left panel shows a variation of electricity demand under various settings. We characterize the hybridization level using motor fraction, which is the maximum thrust desired from electric motor, with the remaining thrust provided by the conventional engine. So there are a few interesting things to notice in the left panel. You might expect with a higher specific energy of the battery energy requirement to decrease, but it is not the case here. The reason is with a higher battery specific energy, more energy is stored on the aircraft, so it can cover a longer distance. That means more portion of the conventional aircraft can be shifted to the electric one, so it actually will consume more energy. And this statement can be demonstrated on the right panel, where I plot the portion of revenue passenger miles can be covered by hybrid electric aircraft. So you can notice with the growth of battery-specific energy, the portion of revenue passenger miles grow.
What does that mean, revenue passenger?
It's just the number of passengers times flight distance in miles. So this is a metric that can characterize how much flight demand can be shifted to hybrid electric aircraft.
So it's not revenue per passenger.
It's not revenue per passenger.
Miles times
Yes.
passengers.
Yes.
Kind of odd to say revenue.
Yeah.
The name is weird.
Well, and the abbreviation is even worse.
RCA. The passengers are rotating.
We further analyzed the daily peak demand at O'Hare International Airport. And for example, when we have a motor fraction of 12.5% and the battery specific energy of 500 watt-hour per kilogram, the median of peak demand would be around 70 megawatt. When compared with the average demand on O'Hare in 2002, it's just 50 megawatt. So the daily peak demand will increase significantly when we integrate the hybrid electric aircraft. We also plot the daily power consumption profile to demonstrate the bottom three panel shows the variation under different battery-specific energy assumptions, with a fixed hybridization level being 12.5%. And you can notice from this graph, the power requirement will also increase greatly with the improvement of battery-specific energy. And if we just look at one day on the right top panel, we would notice the average daily demand would just half of the daily peak demand, which gives the opportunity of scheduling the hybrid electric aircraft charging scheme. Apart from power requirement, we are also interested in how electric aircraft are going to impact jet fuel industry. So first, I break down the fuel consumption in in 2018 by aircraft class, flight distance, and aircraft model type. Since we are only interested in regional jet and narrow-body aircraft, we notice it consumes around 50% of the commercial transport aircraft fuel consumption. And because the annual travel demand is going to increase, so we make the jet fuel demand projection to the year 2050. The left panel shows variation of fuel consumption under different hybridization level and battery-specific energy. The red line stands for the conventional fuel consumption of conventional aircraft. You will notice there's a crossover point between the blue line and red line, which means under the battery-specific energy of 1,000, the hybrid electric aircraft is going to consume even more jet fuel than the conventional one. The reason is with a lower maximum range, the efficiency will decrease, so it's going to consume more energy. Also notice with a motor fraction of 50%, the jet fuel demand is going to decrease most. So we further analyze, setting the motor fraction being 50%, what will happen in the year 2050? So we first make a projection of jet fuel demand to the 2050, where no electrification happens. And then for the flight distance that can be covered by electric aircraft, electrification happens. But for those with longer distance, the jet fuel demand is still going to remain the same. Under this scenario, the jet fuel demand will still increase by 30% compared with year 2018, will decrease only 7% with the case 2050 where no electrification happens. This implies the aviation will still rely on jet fuel. So far, people have been talking about electric aircraft will help reduce carbon emissions. So we analyze how much carbon emissions reduction can be achieved by shifting to hybrid electric aircraft. And our result shows it can only be reduced up to 3.6%. But if we conduct the same analysis by replacing the hybrid one with an all-electric commercial aircraft, the carbon emission potential is more optimistic, as it can reduce up to 56% of carbon emissions. A few things to notice here is a better situation can be envisioned with an integrated design method of electric aircraft and also the lower carbon footprint of electricity generation side. And as I have mentioned earlier, the timing of electrification is very important. And the NASA has predicted a 400 watt-hour per kilogram battery is an achievable goal by the year 2025. So we try to using this near future battery and only use the battery as energy source during takeoff and climb missions. Under such case, we perform the same analysis, and it shows the daily peak demand is much mild compared with the hybrid electric, where we use battery as energy source during the whole flight mission. To sum up, because of the timing of technology development, in particular the battery-specific energy, in the near future case, where the battery is assumed to be 300 watt-hour per kilogram. And if we only use the battery during takeoff and climb only, this will not be a huge challenge for the current power grid. But with the improvement in battery-specific energy, we might want to use battery as the energy source during cruise, and our analysis shows there will be a substantial increase in peak power demand and the total annual electricity consumption. Thank you.
Questions?
So for this analysis, did you, I guess, I work in electric motors and I'm interested in power electronics, and we've been working on making high specific power things for that. For this analysis, did you think about the weight of motors, power electronics, power distribution, any of that sort of stuff, or is that small enough that it wasn't worth worrying about? Or
I don't think it's a small problem, but currently the bigger one is the battery specific energy. So I just focus on the assumption on battery. And
yeah, I think it's likely that that's going to be far more limiting. So makes sense.
Can you elaborate a little on what the motor fraction represents? Is it
It
a percentage of thrust or?
it's the, there are different ways to characterize the hybridization level, and the one I use is the maximum thrust provided by electric motor and the ratio, and with the remaining provided by the conventional turbine.
I was at some seminar, I don't remember where it was, but the person said that our electronics weighs as much as the machine.
Mhm.
Was that here?
That sounds believable to me. I don't
Yeah.
know if you heard it here.
I still find that hard to understand, but there's no transformers anymore, right?
Yeah, so
We're just talking,
I would assume the power electronics should weigh less, but not order of magnitude less. And if you're including cabling and like moving the power around, if you include that with the power electronics, then it could come out.
I was also curious about supercapacitors. I realize that they don't have the same storage, but still, they're a lot lighter weight, I would think, than a battery. Any future in supercapacitors? Or no?
I think supercapacitors are very good at high power, but not great at high energy per mass. So if you had a peak power demand that you were struggling to meet, throwing some supercaps on could help meet a brief peak power, but they're not very helpful for energy storage. I think.
And for question, I didn't consider this, but my reference, the paper done by Gabriel, they considered the weight of the power electronic and power.
So one quick announcement: Boya did come second nationally in this competition with her presentation.
Not exactly the same.
So not exactly the same. This is an amalgamation of her competition presentation and a paper that we submitted last week. So can you elaborate a little bit on the competition? What is the?
The competition, they asked me to analyze how electric aircraft will impact the jet fuel. So they kind of interested in knowing if the electrification happens and how much of their business is going to lose.
And you came second. This was a national competition.
I think it's a national. It's by. It's a part of a conference. Yeah.
And she came second overall.
Yeah, we first submit a paper a document analysis, and then the presentation.
International means it was at an international location, or the presenter was international?
Nuance thought. Minor nuance. No, she was at Denver.
Congratulations, that's great.
She was at Denver for this 2 weeks back.
Denver, yeah, that's international.
Enough.
I'll put a mile.
I like the way you think.
Celestial.
You left the word.
Yeah.
Oh, he has a question.
Yeah, I had a question for you. So you're considering using the batteries and the electric motors for takeoff and climbing. I would expect that would be a higher energy requirement than during cruising. Is there a reason why you're considering it for takeoff and climbing rather than at cruising?
Because there's a paper at East. It's kind of a well-recognized industry paper. They use that during takeoff and climb. They think it's more reasonable to do so at a current battery performance level. And why? Well,
Is there a way to justify that?
I think the justification for that is that the gas turbine is sized for peak power demand, and that's at takeoff and climb. So if you can size your gas turbine for maximum efficiency and minimum weight based on cruise, and then make up that difference for takeoff and climb with an electric machine, you can then improve gas turbine efficiency across the whole.
Same idea as a hybrid car.
Yeah.
During the cruise, you usually just use the gas
Yeah. Peak efficiency.
but only for acceleration.
Yeah, because that's where the efficiency goes to 5 anyway.
And it also might have something to do with the fact that total amount of energy versus power. Maybe it is easier for electric motor stuff to provide that thrust for a short period, short burst of a large amount of power. But what is required for cruise is a lot of energy, which adds bulk. Unless the battery specific energy density is very high, you are adding weight. So I don't know whether that makes sense. So
When designing batteries, specific power and specific energy are competing against
objectives,
each other.
exactly.
Objectives, yeah. So that may be also part of it.
But I don't know too much about the details of the power requirements versus the energy requirements and how it impacts the sizing to make a meaningful comparison.
Are you a master's student or PhD?
Both has just given me the PhD offer.
So she's an MH student,
OMH.
and then I gave her an offer for she's joining my lab from spring.
Yeah.
Did this analysis include any assumptions about price of jet fuel and price of electricity? Have you thought about that yet, or is that?
I
Sure.
have done analysis and didn't show here. So there has been a paper talking about the price. They focus on the price of battery. They thought it would be 100. Is it showed last in the slide? It should be below $100 per kilowatt hours or watt hours. I don't remember. And also, they talk about the price of electricity, with the assumption that the price of electricity and jet fuel fixed. The price of the battery should be below 100 to make it economic competitive.
Okay. That'd be interesting. I have no idea where we would project jet fuel price and electricity price to go, but that might impact what economically makes sense. But
yeah, I actually showed here. There is a projection here.
Oh, is that what that is?
Yes, on the right.
I didn't really catch that. There are too many. Yeah, this is very interesting.
That's all. Thank you.